Alright, so today is our power lesson. The equation that we use for power is relatively straightforward, but this lesson will challenge you in terms of your ability to make derive new equations from this basic equation. So for example, well, I'll just start here. Power is the rate at which work is done. This means that power measures how quickly energy is being used in a certain time period, or a measure of how fast you're using that energy. So just like we said in our labs and things like that, that change in energy meant we were doing work to the system. Now power is just that change in energy, or that work done, divided by time. So that's why we can set P is equal to W over T, and we know that when we do work on a system, we are adding or taking away energy. So if work is being done on the system with the system, we're adding energy. If it's being done against the system, that's like friction, we're taking away that energy. So P is where power is measured in watts, and that's or joules per second. And W is work in joules, and energy is energy in joules. T is always time in seconds. Now, interesting historical fact. Who invented this, not invented, who discovered this equation, do you think? This knowledge. Look at the units. James Watt, okay? So, remember back to Science 10 with, I'll show you something. What did Watt do? What did he make that's famous for in physics? An engine. What did the engine do? What was it? Why did he need to make a Watt engine?
To get water.
To get water out of the mines, right? What were they using before? Horses. And then Newcomen made an engine, but it was sucky, so Watt's like, I'm going to make something better, okay? So here was our Watt engine, where we had the pistons moving back and forth. So the piston moved back and forth, okay? And so it using different pressure changes. So this was, I'm going to just show can you see it in the video? Yeah. Okay. All right, so Watt engine. So, just connecting the dots here. So Watt was the guy who did a lot of physics study on power. So this is named after him, the Watt. Just like Joule did a lot of work with energy. So anything in energy is joules. Yeah? Cool. Change the world. The Watt engine. Industrial revolution. Yeah. Change the world. Remember that. Watt. What changed the world? Watt. Okay. That was exciting. Okay, again, think about a light bulb. The box always displays how many watts the bulb is. So like a 60 watt bulb. That just means that the light bulb is using 60 joules every second. Okay, so when you're looking at different wattages of light bulbs. Note, power is a scalar quantity, so we do not put direction in there. So let's go right to an example. Oh, wait, let me just say something first. So, like I said, we need to be able to take different equations and put them in here. So you need to be able to remember, okay, well, what does work equal? Force times distance. What does energy equal? Well, it depends on the system. It could be all EK. It could be changes in EK. It could be changes in EP. It could be changes in ES. So we're going to be taking formulas from our whole unit and kind of putting them into this basic formula depending on the question. Excited? Yeah. Well, I am. Okay, so a 60 kilogram student runs at a constant velocity, okay, up a 4-meter incline that is at an angle of 40 degrees in 4 seconds. Calculate the power output. So let's just draw a diagram here. This is at 40-degree angle. Our direction of motion is going up the incline. This distance is equal to 4.0 meters. And then this is our h here. We're not told h, but if the height gained, that would be the height gained. Okay. All right. Now let's write out what we know. M is equal to 60.0 kilograms. T is equal to 4.5 seconds. Our D is equal to 4.0 meters. But we might need our height, so let's calculate our height. How can we find out h here? Trigonometry. Okay. So opposite over hypotenuse. So I'm going to use sine theta equals opposite over hypotenuse. So sine of 40 degrees is equal to h divided by 4.0 meters. So sine of 40 degrees multiplied by 4.0 meters is equal to h. So h is equal to 2.571 meters. Now I can say that specifically this is hf, or my final h, and so hi is equal to 0. Okay, so this is all my information that I know. Well, what am I trying to find out? I'm trying to find out P is equal to question mark. Well, P is equal to W over T, which is also equal to delta E over T. Well, I don't have force, so I can't calculate work, right? If I had force and I have distance, I would be able to find work, but I don't. So I'm going to use my delta E over T. Okay? Now, what is my delta E here? It's moving at a constant velocity, so I don't have any change in EK. So I'm looking for delta EP. Okay? So what I'm going to try and find is delta EP. So this is my first calculation, number 1. So delta EP is equal to EPF minus EPI. What is our initial EP if we're starting at the bottom of the incline? It's going to be 0. So I'm just going to set that to 0. And I know then my delta EP is equal to EP of F, which then is M times G times H of F. So delta EP is equal to 60 kilograms times by 9.81 meters per second squared times by 2.571, etc. meters. So our delta EP is 1513.397 joules. So now we can calculate our P. So this is step 2. How it's not EK? Because it's a constant speed, or a constant velocity, it says. So there's no change in velocity, so then there's no change in EK. So number 2, P is equal to delta E over T. 1513.397 joules divided by 4.5 seconds. So P is equal to 336.30 watts. So to sig digs, 3 3.4 times 10 to the 2